he's got many contributions and major contributions in micromechanics and scale. Maybe talk some results he obtained on this topic. And it's also in the scientific committee of the GDR, and we are really pleased to have a talk from Bernard today in our video.
So I will talk today of an idea I have many years ago about how to build a constitutive, a phenomenological constitutive law from a change of scale. So it is not a new idea. I think that many people have had this kind of approach because we know that the behavior of granular material is complex, and it is very difficult to have good modeling when you consider very complex loading path. So the idea is to use a change of scale approach. After, the question is what is the local level, what is the relevant local level. So 30 years ago, I was thinking that the good level was the contact level, as other authors. And we work on this approach, and after some work on this approach, we find that this I think that I don't have the good okay. I think I don't. Okay, so after this some work on this local micro level being the local level we have considered, in fact we have we consider that it was not the good level to be considered at the local level, and we choose to consider a local array of particles, which is called usually the meso-domain. And I will try to show that this level give much more better result. So for this we have performed a numerical simulation using a classical distinct element method code. You have here the different parameters of this simulation, very classical simulation, and we obtain also very classical result at the macroscopic level. You can see that for the loading path you have a mechanical behavior of dense granular materials, and when you perform the unloading path, you have something which looks like the behavior of a loose material, which is very classical also. So now how to define this change of scale from this result. So first, we use some convention. Compression stress and strain are positive. There is no rotation of principal axis, and we define what we call the compression path as the direction where the increment of the deviatoric part of the stress is positive, and the direction 2' is the perpendicular direction to 1'. So some result at meso-scale. So we use some Delaunay triangulation, and from this Delaunay triangulation it is very easy to define the meso-domain which are closed loop of particles in contact. There is two ways of defining this meso-domain, but very easy to define in 2D. Then we define the texture of this meso-domain considering what we have called a loop tensor, and you have the definition here of the loop tensor. It is not completely classical. We have had some element in this definition, and from this loop tensor we can define the global orientation of the meso-domain here with this major principal direction of this loop tensor, and the elongation ratio, which is defined here by from the principal the value of the principal term of this tensor. So after what I think was new is the classification of the meso-domain, and we have chosen to use 6 phases defined by meso-domain sharing some common texture characteristic. We have choose 6, but we can choose more if you want. But for our demonstration here, we have choose 6 phases. So the first decomposition is between the strong meso-domain with strong elongation ratio and with weak elongation ratio. The difference between the strong and the weak is that the strong has an elongation ratio greater than the mean value of this elongation ratio, and the weak has values less than the mean value of this elongation ratio. And after this, we have chosen 3 orientation. One orientation, second orientation, and the last orientation. So 3 orientation, 2 value of elongation ratio, and we have defined then these 6 phases, and we will work on these phases. So you can see the evolution of the texture of this meso-domain during the loading and during the unloading, and you can see very clearly that this meso-domain take a preferential orientation in the direction of the compression, and this is the same for the unloading. So you are starting from here, and you are going for the unloading with preferential orientation in the direction of what we call the compression direction. So now this phase, the volume amount of this phase are not constant. During the loading, you have a great evolution of the volume amount of the phase. And you can see, for example, for the class S, that the class oriented in the vertical direction, the volume of the phase in the vertical direction increase, and the volume of the phase in the extension direction decrease. At the beginning of the test, the volume of each phase the volume of the phase are equal. So we can also define some geometric anisotropy of the phase, and you have here the definition of this texture tensor given from the orientation of each meso-domain in a given phase. So this is easy to define the anisotropy of each phase, and this anisotropy evolves all along the test. You can see here the first point, very interesting point, is that at the beginning the sample, the global sample, is isotropic. But each phase at the beginning of the test are anisotropic. So at the beginning of the phase, due to the definition of the phase, each phase has a given anisotropy, and this anisotropy is increasing for the class in the compression direction. This phase at the beginning has an anisotropy which is negative, and it is increasing, but it is not reaching the zero value.
But now it means that the initial states of the samples are not the same.
The initial state of the sample is isotropic, but in the sample there is different phases, and each phase at the beginning is anisotropic.
Why it is not possible to make material with each phase at the same with the same isotropy at the beginning? It's not possible because
I think it is not possible because the phases are complexly mixed. Yes. So it is, and we have analyzed the position, the geometrical position of each meso-domain, and the phases are completely at random. They are not localized. There is no localization of the phases. The phases are geometrically at random in the sample.
Sorry, just for understanding, for you phase is one geometric pattern of grades.
Is a part of
L, K, and K to get a loop. This is for you one phase.
No, a meso-domain is a closed loop.
Okay.
And I mix all the phases with the same texture characteristic I have defined before. That is the orientation and the elongation.
So for you one phase is one of these patterns.
One phase is a different meso-domain which are sharing the same texture. So in a sample there is several thousand of each meso-domain of the meso-domain in a phase.
It's a class of granulars.
Is a class. We can perhaps it will be a better.
So a class of grain loops.
So you have a model with infinite phases.
We can have, an infinite phases if you want, but to have a presentation, I have only 6 phases. I define 6 phases, but you can take more if you want. So this is the porosity of phases. You can see that also you have the porosity which are different for the different phases. Now I consider the definition of meso-stress and the definition of meso-strain. The definition of meso-strain is very easy. I don't will talk about this. It is very classical. For the meso-stress, it is more difficult. So we have here a meso-domain. This meso-domain are defined by several particles in contact. So we have different ways to define the stress in this meso-domain. We can compute the stress in each particle and take only a part of the particle and to have some mean of the stress due to the stress in each part of the particle. It is not the way we have chosen. We have considered that this meso-domain is in equilibrium under all the force acting outside all the particles which are around this meso-domain. So we consider that the equilibrium of this meso-domain is governed essentially by all these forces which are outside the boundary of, not the boundary of the meso-domain, but this boundary here. So we have considered that we can define the stress with the usual formula to define the stress from some local forces, and we choose to consider that this stress is also the stress we will consider in the meso-domain. So it is an hypothesis, but we can see that after we can have some information of the accuracy of this hypothesis. So you can see here the evolution of the stress ratio for all the class, and you can see that each class supports different level of stress.
Sorry, I don't want to interrupt you, but so if by chance one grain goes away and the other grains goes, you have a change of phase.
Yes. All during the loading, at every step of calculation, I have to compute all the meso-domain, and this meso-domain change all along the stress path. So you can see here the evolution of the strain ratio also, which are different from different classes. For example, here I have dilatancy, and here I have contractancy. So now I have rebuilt the global behavior the material using the definition, the local definition I have proposed. So I use the stress I have proposed, the strain I have proposed, and I take the volumic amount of the stress and the strain, and I compare this value with the boundary value. So it is only to analyze the validity of the initial hypothesis, in particular on the variable I have used for the stress and for the strain. So this is for the stress ratio, this is for the volumetric strain, and you can see that we have a very good agreement between this definition from the local value and the boundary value. That is to say that I think that the variable we have defined are relevant. So now, so we can give some first conclusion. Relevance of the considered variable at the meso-scale. Class S can develop much more anisotropy than class W. The texture and the behavior of the phases are depending on their orientation with respect to the loading. So now I have a step more. I try to model the behavior for each phases. So for this, I take a very classical elastic plastic model I have developed in the years 1986. It is prehistorical. So it is a very classical elastoplastic model, but what is very important in this model is that we use a kinematical hardening to take into account the induced anisotropy. And you have seen before that this induced anisotropy is different for each phase. So it is a key point in this modeling. So I will not enter in the different relation of this model, but you can use this model, or the model will give also the same kind of result. So you can see here. So a little point, we have to change a little bit the model because the kinematic hardening we have chosen at the beginning what was not able to take into account the initial curvature of the curve, the stress strain curve. So we choose a parameter R, which is included in the kinematic hardening model. We choose to have this parameter depending of the current anisotropy, and this provides a better agreement of the model with the curve we have simulated by DEM. So now we have to identify the model constant of each phase, and we give this identification. There is no difficulty to define the different constant of the consider model for each phase. So we have 6 models with 6 set of constants for the 6 phases. Then we have a good agreement. As in the model, we don't take into account some softening. We don't have a very good agreement at the end of the loading, but it is not very difficult to add this point we can improve this point very easily. So this is for yes, this is for the strain ratio. So for this moment we have only defined a model for the phase. Now, is this model can be applied for all the stress paths? So what we call the validation of the model at the meso-scale. So we use now, after this point, we use only the model we have identified in the loading stress path. So we don't have any other identification after. And we try to define the unloading path. And you have seen at the beginning that for the unloading paths, the behavior was different. The loading path was corresponding to more or less dense materials, and for the unloading path we have the behavior of a loose material, more or less. So for this we make some hypothesis to generalize the model. The two hypotheses is that the parameter governing the general behavior of each phase depend on the orientation of this phase with respect to the compression direction, and that the parameter which governs the behavior at the beginning of the new loading path depend on the anisotropy at this change of orientation of loading parameter. There is only one, it is U. So from these two hypotheses, we try to define all the parameters for the phase during the unloading path. So we...
Sorry, I disturb you with stupid questions, but I try to understand. You have found Young modulus and Poisson for every phase.
Yes, in particular.
Then can you build the complete elasticity tensor knowing which are the phases and which are these Young moduli?
No, for us, the elasticity in granular material is not the topic.
You talk about Young modulus.
Yes.
I mean, not with you, not me. Young model means elasticity.
Yes.
All the phases are not in elasticity.
But I am in this, we can in some case deal with the elasticity of granular material, but it is not the topic of this talk. It is essentially how to model the plasticity. The plasticity.
Okay, so what it means, Young modulus? Yes.
Young modulus? Yes, yes.
This is a
but in this case, we consider, which is not the case, we consider that the elasticity was an isotropic elasticity. It is isotropic elasticity, and we consider that the Young modulus and the Poisson ratio of each phase are the same. So it is it is not, this is, we can improve this point, because I agree with you, it is an hypothesis which is not realistic. But in granular material, it depends. If you are working at very small deformation, you have to deal with elasticity, but if you are working at 2%, 3%, 10%, elasticity is not important in this case. So I consider here that elasticity is not important. So I have defined here all the plastic elastic parameters the same for the loading path, and for the plastic model I can define all the parameters from I arrive to the end. So this is the forecast for the all-loading path defined only from the parameter which has been defined for the loading path. And you can see that at the level of the phase, the agreement is correct. There is some problem at the end, as in for the loading, I have not softening in the model. So this is for the strain ratio, and now I will build the meso-scale. I will build the macro result from the meso-scale result for the unloading. So for this, I have to define the evolution of the volume of each phases, and for this I choose to have a very simple model taking into account the distance to the critical state, and we can have a very efficient model for the evolution of the amount of volume of each phase. And now it is evolution of parameter alpha we have defined previously for this model, and you can see that this can be defined in relation with the distance to the critical state anisotropy. So you can see here the forecast of the volumic amount for the unloading. This is a forecast from the parameter has been defined for the loading, and we obtain this evolution of volume for each phase. And you can see here the final result. You can see that this is the forecast for the unloading, and this is the forecast also for the unloading this is for the strain ratio and the stress ratio at the elementary representative volume. So, you can see that with the knowledge only of the loading, I can define the behavior for the unloading. So, in my opinion, we have shown from this study the relevance of the change of scale approach considering a meso-scale. So now remains to define some new constitutive modeling of granular material, taking into account this definition of local phases or local classes. Okay, thank you for your attention.
Yeah, but I think you have progressed since last time I heard you. But I still have, if you consider not the material, but the real material, the granular material, do you have an idea, or you can identify your meso-scale parameters to obtain the macro-scale behavior?
Yes, yes, it is clearly what we have to do here. So I think it is as all the model we have been defined many years ago. For example, the crystalline plan, which have been considered. So I think that you can use some, for example, loading path. You obtain the global behavior, and I have defined here some consistency equation with two parameters, which has orientation of phase with respect to the compression direction, and at the beginning the anisotropy. If you use a model which include the evolution of anisotropy, you can have some information, and you can perhaps define this local behavior. But I have some idea, but it needs work to yes. I think it is perhaps possible. But I think I was this analysis is to show that if you can do that, you can obtain a macro.
This is impressive.
It is. That is to say, is it interesting to work in this orientation of work?
I have several questions. I'll try to compact them. I found your presentation very interesting. However, I did not understand clearly some details. So, for instance, is there some arbitrariness in defining the meso-domain? Because if you have a group of particles, and if you want to select the meso-domain, you have several choices probably.
No, if you are, it is. You don't have any. You use first a triangulation of Delaunay.
Okay.
This is unique. No, it is not unique. And after you consider the domain sharing some in this triangular you have this corresponding to a contact, and this corresponding to particle without contact. So you see, I can add this to this, I can add this to this, and I can add this to this. So you have here a meso-domain, and it is unique the way to define this meso-domain.
But how many different types of particles are you considering spherical particles?
We have worked on this domain with angular particle. It is the same.
Yes, but so just the size of particles is fixed a priori. In the sense you have some discrete number of different size of particles, or in principle you can have any number.
We defined the center of mass of each particle, which is unique. Center of mass.
Okay, so this is not a kind of discrete model.
It is.
It is not a model where you predefine the size of the particles.
Yes. It can be used for any kind of size, and we have used for angular particle.
The last question is, did you also try to see the response to many cycles of loads? Because I'm expecting that at the beginning of a loading and unloading cycle, you obtain a different pattern, and so if you start loading it, you should get another, and so maybe you have a kind of limit cycle at the end of the loading process after many.
We don't try. I agree with you that the behavior of the material will change all over the cycle. So I hope that this procedure can be used until a certain number of cycles, but I have to try.